It is my great privilege. I'm very excited to introduce Byron Wallace from Northeastern University. We're thrilled to have him. Byron is an assistant professor at the Khoury College of Computer Science at Northeastern University and an adjunct at Brown University. His research is primarily in natural language processing methods with an emphasis on their application in health informatics. We all know how important processing health data is these days. Byron also has this tendency to release software that's related to analyzing literature related to bio informatic to bio medical applications. I urge you to, if he's not going to mention this himself, look up something called Robot Reviewer, which is an aggregator website for biomedical literature, which is, you could drop in the PDFs and it gives you a summary of everything that's in those papers. A very important application. And no more further ado. So Byron, the floor is yours.
Okay, cool. So thanks, Yuval. Thanks so much for the very nice introduction, and thanks also for the invite. I'm super happy to be here, even if here is the internet, and I am forcing you all into yet another video call. So what I'm going to be talking about today is some work that I've been doing with collaborators on trying to design, methods that allow us to better understand how it is that these neural models and NLP come to make the predictions that they do. Okay. So just sort of by way of motivation, no surprise, I'm sure, to most of you on this call, if you look at the sort of state of NLP in 2020, what you see is this trend toward ever larger models, right? So this is a plot that's showing sort of model size on the y-axis, number of parameters in log scale, and time on the x-axis, and sort of popular and influential NLP models that have been introduced over the years. And you see this kind of continued trend towards ever larger neural network models. And this has afforded progress in the sense of, you see numbers on leaderboards ticking up. And there's no question that huge advances have been realized, partly as a consequence of this trend. And so in terms of how these models are used, the way that I think about it is, you're going to kind of take in some input text, some input piece of text, and run it through some sort of black box encoder. And the encoder, this is probably going to be some very deep neural network, usually pre-trained, and it's going to hand you back some vector representation of your input, x, right? And, subsequently we can make a prediction y hat on the basis of that representation. And in terms of the actual encoder architecture, way back in the day, we used to use recurrent neural networks a couple of years ago, things like LSTMs and GRUs, and of course, more recently, there's been sort of a marked shift towards transformer architectures. But in either case, these are networks that will yield contextualized representations of constituent words in an input. I'll also refer to words as tokens in this talk sometimes. And then we can kind of pool over those representations to derive let's say a document representation, which is that X I referred to before. Okay, so again, this has certainly afforded progress, but there is this issue, which is that we really don't know what X is encoding, right? And so consequently, we can't really say what led to a particular prediction y hat. And I think, perhaps the most natural first question to ask is, so what? Like, should we care? And I would say that there are plenty of applications that I can imagine where you probably don't care, right? Where maybe it's enough to have strong empirical performance, and how the model is making its predictions is perhaps not terribly important. But I mean, there are conversely many cases where you care very much, right? And so you've all mentioned that a lot of my work, for example, on the application side is in sort of the space of health broadly. And this is a setting in which you very much want to have at least some notions of, I guess, interpretability or transparency to establish trust between, let's say, a model and a domain expert that might use that model. Also, I guess more broadly, there are sort of obvious fairness implications if you think about things like sort of systems that are doing automated resume screening or something like that. You know, there are settings in which you very much would like to be able to know what is informing particular predictions, right? And a last point that's related to the fairness question, I think, is that a recent conversation in NLP has been about the fact that our training data, these things that kind of underlie those leaderboards, is maybe not always so great, right? And I think this is a consequence of how we compile these data sets. Usually this is done automatically or semi-automatically and with some combination of crowdsourcing. And what happens is artifacts are introduced into these training data sets such that over-parameterized models exhibit strong empirical performance, but maybe aren't learning what we want them to learn. And I'll talk more about that later. And I think the point about interpretability here is that it's difficult to appreciate when that is happening when we have these very complex and kind of black box architectures. Okay, so that's really all I'm going to say in terms of, I guess, broad sort of motivation. And what I will do with the remainder of this talk is speak to three different, I guess, lines of work that kind of approach this problem of interpretability for NLP models in different ways, right? And so the first kind of line of work I'll talk about concerns what are sometimes called rationales. So these are basically highlighted snippets of inputs, and this is perhaps the most obvious and intuitive way of trying to provide justification, let's say, for system predictions. The second bit of work that I'll talk about is an alternative kind of view on explanations, which is the use of influence functions for NLP specifically. And in this paradigm, what we're going to try to do is basically try to explain predictions by tracing back to training examples in our training data set that most informed it. And finally, I'll talk very briefly about some work that we've been doing as well on trying to better understand how sequence tagging models make the predictions that they do. So these are models that are doing things like named entity recognition, where you're making predictions about individual words in an input sequence. And in particular, I'll focus on the degree to which these models tend to focus on sort of the context in which, let's say, names appear versus the sort of verbatim names themselves. Okay, but I'll start with this kind of first line of work on these rationale things, right? So here is a not terribly sort of exciting application, which is sentiment analysis over movie reviews. And maybe what we want to do is classify these things as positive or negative, right? And so the idea behind rationales is quite straightforward. What we're going to do is we're going to basically make our prediction or make our categorization, in this case positive, and then as support for that categorization, we might highlight, for example, the phrase, "the acting is great," right? And in some sense, we take this as a justification for that classification. Just to show, I guess, an example of a slightly more interesting and compelling use case, or at least what I think of as a more compelling use case, here is a snippet from what is in fact a very long article that describes the conduct and results of a randomized control trial. And in this evidence inference task that we've been working on for a while now, the idea is to basically categorize articles as presenting evidence that a treatment of interest either significantly decreased, had no significant difference, or significantly increased some outcome of interest as compared to some comparator treatment. And in this case, for example, perhaps the categorization is that the trial that's being described reports evidence that there's no significant difference between these treatments of interest. And that's what's underlined here. And the idea would be to provide, out of this long article, you want to provide evidence that kind of supports that categorization, right? So this is the general idea of I guess, rationales. And this idea, this notion, has been around for quite some time now in NLP. actually the first work of which I'm aware that really kind of used rationales as we think of them in NLP was from Zaidan and colleagues way back at NeurIPS 2008. And this really, I think, inspired a whole line of work that followed on top of this, including my former PhD students, for example, in which back at EMNLP 2016, we were trying to kind of bring some of these rationale augmented methods into the kind of neural era as neural networks were beginning to reemerge as the dominant class of models in NLP. And I guess what I would say about a lot of this kind of prior work on rationales is that most of it assumed that we had access at training time to basically manual annotations of rationales, right? So the idea was to integrate those labels, basically that complementary supervision, into training such that you would improve the predictive performance on the downstream task, right? But I think what's happened is as we've transitioned to increasingly complex models, there has been a heightened interest in trying to design approaches that basically allow models to provide some sort of feature attribution at test time, even when you don't have access at train time to sort of explicit human rationales. And so one way that you might try to do this is you might try to use an attention mechanism, right? So in attention mechanisms, what we do is we define a parameterized module that is going to take in hidden representations that correspond to our inputs and that are yielded from our encoder. And we're going to score those where the score should be proportional to, I guess, how useful those hidden representations are going to be for performing whatever downstream task it is that we're performing, for example, sentiment analysis. And usually we normalize those scores into a distribution, and this is what's denoted here by alpha. And then we kind of compose a context vector C by taking a weighted sum over the hidden representations where the weights are the attention scores. And the C vector is the thing that we make a prediction on the basis of. So if you do this, what you can do is you can assemble kind of a heat map or a saliency map that looks a little bit like rationales usually. And what you're going to do is you're going to highlight the words at each position in proportion to the attention scores that they were accorded, right? And so there's a couple of problems with doing this, right? So the first problem, I guess, is that the attention scores, this alpha thing, is soft, right? So it's continuous. And that's because it's a distribution. And so every hidden state will receive a non-zero weight. And that means that every hidden state will have, in some sense, influenced your context vector. And in addition, it's the case that the attention scores are not necessarily kind of aligned with your inputs in some way. What I mean by this is, in the case of contextualizing encoders, so something like a bidirectional LSTM, which is what I show in this picture, but also with something like a transformer, the hidden representation that you get at index J actually bakes in information from sort of all of the tokens, all of the words potentially in that sequence, not just the word at index J, right? And so what this means is that the attention score that you get reflects not just the influence specifically of word J, but also its interactions with all of the other words in the sequence. But then when we kind of draw the saliency map, we highlight tokens in proportion to the intensity, in proportion to the magnitude of the attention weights for that index, right? And that's a little bit confusing in some ways. So anyway, a while ago now, my PhD student Sartak set out to kind of interrogate, I guess, the relationship between model inputs, attention weights, and model outputs. And we found a few things. So one is that attention weights correlate only kind of weakly with more standard feature importance measures. So these are things like gradients or leave one out scores. Leave one out scores being where you remove an input word and then calculate the difference in output that this induces with the original prediction. And also, it is the case that the model output is actually often pretty invariant to the attention scores. And what I mean by this is you can do things like you can permute the attention scores that you get kind of at random, and in a lot of cases, this actually won't affect much what the model output ends up being, right? So this kind of calls into question, I think, the use of attention as kind of reliable indicators of feature importance. In contemporaneous work, Sophia Serrano and Noah Smith asked a similar question and kind of found similar things. I think in their case, what they were doing is zeroing out inputs in rank order of the attention weights that were induced for them, and recording sort of how many times they had to do that before the decision or the prediction basically made by the model kind of flipped, and found that it was quite a few. And I think there's been some additional work since then that's investigated similar things and come to qualitatively similar conclusions. That said, your colleagues here at Georgia Tech, Yuval and Sarah, came along and pushed back on this a little bit, and they made a number of really nice points. So one of the points that they made was, look, attention scores might not sort of necessarily always provide us with meaningful feature attribution, but in some cases they might, right? And they outlined some, I guess, tests basically that are intended to assess the sort of whether and when it might be appropriate for a particular data set or task to use attention scores in this way. And the other thing that they did was try to clarify terminology a bit. So if for anyone that is sort of listening and has worked in interpretability, you know that nobody seems to agree on terminology, and that's actually quite a hindrance to progress. And in the context of NLP and rationales, I think one thing that's really important, and this again was a point made by Sarah and Yuval, is that it's sort of critical to differentiate between sort of plausibility and faithfulness, right? And so by plausible here, we mean that a rationale is somehow agreeable to a human. So if you show a snippet in support of a particular categorization, plausibility refers to whether the human is likely to say, yeah, that makes sense, basically. And this is actually separate from this notion that I think I've sort of had in mind, at least implicitly, which is faithfulness. And so faithfulness says that to what degree is the rationale that the model presented, to what degree did the model actually use that to come to its final prediction, right? And so this is a quality that, the degree to which you care about these things will depend very much on the application that you have in mind, right? But there certainly are cases where you do care about being able to produce, I guess, faithful rationales in the interest of model transparency. And so with that in mind, we ended up teaming up for an ACL paper this year where we attempted to design a framework that allows for faithful rationales in the sense of being discrete extractions from inputs, and in a way that's sort of easier than prior approaches to doing this, right? And in particular, we were really inspired by this work from Tao Li and a group at MIT from 2016, where the way that they went about basically inducing discrete rationales is by defining sort of two models. One I will call the extractor network, although I think they call it the generator network. And the idea is that the extractor network is going to perform a discrete selection of input words or tokens, and then those sort of tokens are passed forward to a predictor network, right? And the predictor network is going to make its prediction, right? And this discrete selection, rather in place of kind of continuous scores, sidesteps some of the complications that I mentioned earlier that are sort of inherent to using, I guess, continuous saliency scores, right? And so this is nice. So discrete selection has some nice properties in this sense, but it's also the case that because it's discrete, it's no longer differentiable, and so training is difficult, right? And so in general, this means that you have to sort of rely on things like reinforcement learning, so something like reinforce, And that sort of works. So basically the idea is you're going to, I guess, sample from your extractor network or from your, I guess, generator network, if you want to call it that. And what you're sampling here is like a binary mask over inputs. That's Z, and you're going to try to sort of minimize the predictor's loss in expectation. And the problem with this is that, and I'm sure those of you that have worked with reinforcement learning in general know, this is sort of high variance, right? So it's also just kind of finicky, right? Like it's hard to train these things in a way that's, I guess, reliable. So this is an issue. Some alternatives have been proposed. There was some very nice work by Bastings on differentiable binary variables. And in particular, the idea here was to use the reparameterization trick. And this is quite nice, but it also is a little bit finicky to work with. There are sort of issues with convergence during training and things like this. So what we set out to do was we wanted to provide sort of flexible framework that enjoyed, I guess, the properties of providing discrete rationales, but also makes kind of implementation easier and sort of has lower variance in terms of the parameter estimation. So that was kind of our aim. And what we ended up coming up with was this thing that we call faithful rationale extraction from saliency thresholding. And the idea is basically to have a number of different models that are responsible for different things. So the sort of first model, its only purpose really is to induce some sort of continuous feature importance scores. And this can be done using kind of any mechanism you like. It could be feature gradients or attention scores or some scores derived from Lime. But the key is to discretize these. So basically we're going to just use some rules on top of these sort of soft scores to convert them into binary labels over our tokens or words, right? And so you could do this in various ways. So if you imagine that our saliency scores, our continuous scores, are reflected in this kind of heat map here, you could imagine, for example, saying I want to take the sort of the best sequence, which is contiguous and of length k, where k is sort of the desired rationale length, such that I maximize the saliency mass overall, with respect to all other potential runs of length k, right? And in this case, you would get this opening snippet of text. Or you might, for example, say what I want to do is I don't care about contiguousness. I just want to take the top k words, and you could do that as well, right? So there are several ways that you can imagine doing this. These are sort of the most obvious. But the thing is once you do this, what you can do is you could train a separate model that's going to be basically a sort of named entity recognition type system, which is going to score or label each word in the input as being kind of a yes or a no. And you can train this using the pseudo labels that you derived in the first step. Okay? And this will yield X tildes, which are these kind of compressed inputs, basically. And then you can finally train a prediction network, again, an independent network. And this network only ever sees the inputs that are sort of compressed from the extractor network, right? So you only get the X tildes, basically, right? And so this is a very simple way, I guess, of sort of realizing discrete selection over inputs, right? And the other thing I would point out about Fresh that we think is kind of nice about it is it's quite flexible, right? So you can imagine, for example, using various, you can sort of use any feature importance score setting that you would like or approach that you would like for step one, and combining this with various kind of heuristics that you try to be clever about. You could even, if you were being kind of extreme, you could sort of drop in for the extraction network, you could actually just drop in like an off-the-shelf summarization system. We haven't tried that, but you could. In any case, we looked at the, we sort of compared this approach to that reinforce approach for discrete rationale selection I mentioned earlier. We also in the paper have results where we compare against the differentiable binary variable approach as well. But basically what I'm showing is the performance in terms of macro averaged F1 score on the y-axis here across I guess, 5 different data sets that span a variety of different domains. And I'm showing the performance that's realized when you ask for rationales of different length. So for example, in SST, the leftmost plot, which is, I think, a sentiment analysis data set, we're looking at cases where we ask for rationales that comprise 10% of the input and 20% of the input. And what we see is that this fresh approach tends to do actually a bit better than using kind of reinforce. And moreover, it does so with lower variance across 5 random seeds, which is how many times we repeated it here. And the variance is described by the minimum and maximum values that were observed across these runs, and those are the vertical bars, right? And so basically there's very little variance for fresh, right? Whereas, as we would expect, reinforce has sort of high variance, right? So discrete rationales have these nice kind of inherent properties, but one thing that we don't really know is whether they're actually kind of found to be plausible. So do humans actually find them, I guess, intuitive, right? And so we set out to also evaluate this. And in particular, what we did was, in our 2-model framework, we replaced the predictor network with a human, right? And in particular, what we did was we went out to Mechanical Turk and we asked folks to perform the sort of end classification tasks. So for example, sentiment analysis, although we also did this for a question answering data set as well. But, so we sort of asked them on the basis of this text, which is a rationale of some sort, what sentiment does it convey? And how confident are you in that answer? And we also asked them about kind of readability of the text. And the first thing that we did as sort of a sanity check was we took a data set for which we had rationales that were provided by other humans, and we asked the Mechanical Turk workers to perform this task on the basis of those. And perhaps unsurprisingly, they're able to do this with almost perfect accuracy and with reasonably high confidence. If you just show them kind of randomly selected tokens, IID randomly selected tokens, or spans, you get a pretty considerable drop in accuracy and also in sort of confidence. And then, if you compare sort of the reinforced approach with this fresh approach, in terms of the accuracy, I guess they did a little bit better when they got the snippets that were extracted by the fresh variant we used. But I would say the confidence is sort of a wash between the two. So on plausibility, I'd say, we're probably at least equivalent. And so that was kind of nice to see. And we also have results. This is results on the movies data set for sentiment, but we have similar results on a sort of a QA data set. All right, so just to summarize, I guess the sort of fresh approach, this is kind of a general framework that's intended to provide discrete rationales, and so faithful in this sense, in the sense that we know what the predictor network used. It's amenable to extensions, as I mentioned. It's also super simple to implement and train, and that was kind of one of the points of emphasis we had. And it enjoys kind of lower variance and stronger sort of empirical performance, at least on the data sets we looked at here. One last note that I'll make on it, though, or on, I guess, really on faithfulness and the notion of faithfulness, is, I suspect our terminology will continue to evolve, right? So Alon and Yoav had this nice piece very recently talking about how, basically, even in discrete rationale selection setups, you still, at least as presently framed, we still don't know sort of why the extractor network selects the tokens that it does, right? And so this can result in counterintuitive behavior. And so I think in this piece, they're sort of talking about how you need to go further and you need to sort of align the rationales with what they refer to as sort of social attribution. So I would point anyone interested to that paper for kind of further discussion in terms of refining our, I guess, definitions and set of terminology. All right, so the last bit of work that I'm going to talk about concerning rationales is this work on eraser. So this was joint work with some folks at Salesforce Research, including Nazneen, who co-led the work with Sartak and Jay, who are PhD students at Northeastern. And the idea here was basically to provide a resource for the community, specifically for sort of developing and evaluating models that can kind of rationalize predictions or provide these snippets. And so this data set, this I should say benchmark, comprises 7 data sets, and all of these data sets have human annotated rationales, right? And you can grab this at eraserbenchmark.com. We span a number of different sort of tasks, so hopefully it's interesting in that sense. We've introduced some metrics. So the metrics that are intended to capture sort of plausibility in the sense that I defined it before are pretty straightforward here, because you can measure agreement with the human provided rationales, right? And so in the sense that measures how much the, I guess, machine generated rationales agree with the human generated rationales. I think measuring faithfulness is a tricky and largely open question. We do define some metrics based on prior work that we think at least provide a starting point for doing this. So in particular, we suggest using what we're calling comprehensiveness. And the idea here is if you have a rationale R sub I that supports the classification of instance X sub I, and basically the idea is that the model M has classified this instance as belonging to class J, then if I subtract that rationale, if I erase that rationale from Xi, I should see a drop in the confidence that I have in the categorization of Xi to class J. That's the idea behind comprehensiveness. For sufficiency, this is sort of the complement of that, I suppose. And what this says is if I feed the model only the rationale, I should still end up with either about the same or perhaps even greater confidence that the instance I belongs to class J. So these are some notions we've been playing around with, but I'd be happy to sort of talk offline or later during the QA about potential metrics that might be better. Okay, so if you're interested, there's code and baseline models that you can start working with the data, and I'd be happy to see what you all do with it. All right, so that's all I'm going to say about rationales. I'm going to shift gears a bit and talk now about this notion of trying to, I guess, explain predictions by virtue of the training examples that most informed them. So this is joint work with Yulia and Han, who are both at CMU, and this also appeared at ACL 2020. So far I've been talking about these saliency maps and kind of feature attribution methods, but a sort of different way of thinking about explainability in NLP, or really in machine learning generally, is to ask, okay, what training examples influence this particular prediction, right? And so rather than kind of generating these saliency maps that score individual tokens, what you might do is go out and retrieve train instances from your train set that sort of most influenced this particular output, right? And the intuition that we had here for why this might be particularly useful for some NLP applications is that my view is that sort of rationales, I think, are useful for many tasks. So things like sentiment analysis, I think it's clear that there's some sort of face validity to rationales. But if you think about something like natural language inference, which is a little bit more subtle, here what we're trying to do is say whether a premise kind of whether a premise is contradicted by or it sort of entails a particular hypothesis, right? Or if these things are neutral with respect to each other. And it's maybe less obvious what we hope that a saliency map or a set of rationales is going to tell us in this kind of two input case where there's a certain amount of sort of, I guess, inference that needs to happen regarding the hypothesis and premise, right? And so we were interested in knowing and sort of understanding if maybe these influence functions would be a way of explaining more complex predictions like in NLI. So influence functions in general were introduced, so influence functions in the context of explaining kind of black box neural models. This was introduced by Ko and Liang at ICML a few years ago. And what these things will do is they try to answer the question, what effect does removing training point I, so xi, yi, have on a particular test prediction y hat? And so this will be mediated through your parameter estimates theta hat. And so in theory, you could, I guess, sort of remove training instances one at a time and retrain your model and get new estimates for theta hat. But of course, that would be painfully and prohibitively slow. Right? So instead, it turns out you can approximate how kind of upweighting a training point I by some epsilon will affect or change the parameters. And it turns out that there is kind of a famous result from the early 80s that basically gives you this quantity in closed form, right? And the only thing I'll kind of remark about this here is just to point out that it involves an inverse of the Hessian, which means it's very expensive to compute. So Ko and Liang, in their original ICML paper, they offer several approximations that speed this up, and we're using those, but it's still very slow, and that's a bottleneck to applying this method. But nonetheless, once you have this quantity, you can kind of chain through to get the effect of the training example on this particular prediction by just looking at how the loss is affected on this specific instance y hat, right? So then what we can do is we can look to see to what degree the sort of influential examples retrieved using this influence function, I guess, agree with qualitatively the story that we might tell on the basis of saliency maps, right? And we were particularly interested as to whether the task mattered, right? Because again, the intuition here is that for something like sentiment analysis, saliency maps are probably more appropriate, whereas for something like NLI, perhaps influence functions provide more insight. This is a little bit complicated, though, because, of course, it's not really even clear what agreement means, right? These things are qualitatively doing different things. So one idea we had, though, was to check whether training instances that contain important tokens, as according to the saliency score that we're using, appear in comparatively highly influential training examples, right? And so, in particular, we were using just input feature gradients as our saliency score. And what we can do is we can go out and we can retrieve, in this case for sentiment, right? This is the sentiment analysis task. We're going to go out and we're going to retrieve all of the examples in our training data set that featured the token or the word that was scored as most positive for a particular test set, right? And we do this for all of the test sets, for all of the test instances that we're looking at. And then we can report the average influence exerted by those instances. So that's that green bar. And we can do the same thing for the median and most negative tokens for each test example that we look at, right? And I think what this is showing is that, as you might expect, the examples that contain the most sort of positive token with respect to the input gradient exert more influence on average than sort of other examples in the train set. So I think that's intuitive, right? However, if you look at the same plot for something like NLI, for NLI specifically, you don't see this, right? So I guess in the former plot, I would say that, qualitatively, the sort of influence function results are sort of telling you something similar to what the saliency scores are telling you. But if you look at this for NLI, you get actually the reverse trend, which is a little odd. And I guess what I would conclude from this is, if nothing else, the influential examples are maybe not telling you the same thing as what the saliency scores are telling you, right? And so I guess the natural question then is, well, what is the influence function telling you? And what we did was we actually sort of looked at some of the examples. So here, I think the model predicted entail, and I've highlighted the red is negative, I guess, salience, and the blue is positive salience. And this is the test input, and if you look at the most supporting training examples that inform that prediction, you get this kind of list, right? And if you kind of qualitatively inspect the examples in this list, what you'll find is that these seem to not really be that related to the test input, except that they feature a lot of word overlap, right? And in fact, this is an observation that has been made previously. So McCoy and colleagues had this nice piece of work where they talked about how these neural models are prone to basically exploiting these shallow heuristics that often succeed. And so one example of that is kind of capturing lexical overlap and using that to basically predict entailment. And this is kind of largely independent of the, I guess, underlying generalizations, right, that we kind of hope these models are capturing. So they actually created this Hans data set, which basically features a whole bunch of examples that explicitly were constructed to exhibit this artifact. And one thing that's kind of cool, I think, about influence functions is that it provides opportunity, or sort of provides a mechanism by which to, in some sense, quantify this, or at least to visualize this, right? And so in particular, what I'm showing here is, for one example in the Hans data set that exhibits a large degree of word overlap, if you plot on the x-axis the influence scores, and on the y-axis the lexical overlap rate, what you see is this trend where the examples with the highest magnitude influence over the prediction that was made here, this entailment prediction, tend to have much higher lexical overlap, right? And so this is kind of a neat way of looking at that problem. And I can imagine kind of using this sort of an approach to, I guess, probe for whether models are exploiting particular candidate artifacts that you suspect might be influencing predictions, right? Here I show it again for like just a different, like a real MLNI example. So this is actually from the standard sort of data set, right? And so this doesn't exhibit as much token overlap, and so you sort of see the effect still, but it's much less, I suppose, which says that in this case it's not relying so much on that artifact or on that heuristic. Okay, so I'm gonna just wrap up with just a brief foray into sequence tagging, but this is shorter than the other components. So the last thing I want to talk about is this work on sequence tagging. And in particular, we'll be thinking about kind of named entity recognition systems. So this is joint work with Ocean Agarwal, who's a PhD student at UPenn, and her advisor, Annie Nunkova, and also Yin Fei, who's at Google. So in named entity recognition, which is kind of a standard task in NLP, what we want to do is we want to recognize entities like person names and organizations and so forth, right? So if we're given a sentence like Jim Jones was involved in a car accident, we would like to identify, Jim Jones as a person name. And what motivated this work was this question of like, well, how sensitive are these models to the specific names that are observed in the data? So for example, if we swap out Jim Jones, which is a common kind of American name, with something like Nagasi, which is a common Ethiopian name, like what effect will that have on the predictive performance of these models? And so in earlier work, we introduced this kind of suite of entity switch data sets, which basically, in which basically we swap out entity names with plausible alternatives from different national origins. And so you can use this to kind of probe what happens if you swap these out at test time to the predictive performance, right? And it's not surprising that you would see performance drop, right? Because you're changing the distribution. But I think it's still important to quantify this and to understand sort of how sensitive models are to the specific names, let's say, that they're making predictions about, right? And just to give a sample of some of the results that we reported in that original paper, if you look at, let's say, just the most far right column, so this is F-score for a BERT-based approach, and for the original Connell test set, I think this is just on person names, you get 97 F-score. If you swap in Vietnamese names instead, you see a drop of like 6 points plus, right? So maybe this isn't great, and it's something that we might think about going forward. And in terms of like what's causing this, I suppose the question is, to what degree are systems kind of memorizing names versus sort of just relying on context, right? I think in some sense we would like models to rely on context to the degree that it's possible, right? Because it makes them more robust to shifts like this. And so we did a couple of experiments. One thing that we did was we looked at a words-only model, which basically does logistic regression on top of glove embeddings, which are fixed. And that's the blue bar. And then we also did a context-only LSTM-CRF, which basically does not have access to the local token or word about which it is making a prediction. And then, of course, we look at the green bar, which is the typical thing, which combines these two. And what you can see, of course, is that context only does quite poorly. It's not surprising that it does sort of worse than the green bar. It's maybe surprising that it does worse than the words only approach, right? We also did this with BERT, where basically we have a version where we only show it the context, so you mask out the token about which you're making a prediction, or the entity tokens about which you're making predictions, versus word in context, right, which is the standard approach. And again, you see this kind of precipitous drop. It's hard to say like how big of a problem this is, though, without knowing sort of how feasible it is to make these classifications on the basis of just the context in which words appear. So what we did was we enlisted humans to try. Basically, we took 200 instances where the context only bidirectional LSTM made errors, and we asked the humans to make the designation using only the context. And actually what we found was surprising, at least to me, which is that this was Connell data. I think they were only able to actually make the correct prediction on the basis of the context alone 24% of the time, so about a quarter of the time. So this is also quite hard for humans. And so, there's only so much there's a little bit of room for improvement there, but I suppose there's only so much we can expect from the models. So, going forward, like maybe it's the case that you basically have to exploit sort of the local, basically memorize the names that you've seen and look for similar names, and that's totally fine. But maybe it would be nice to at least be able to know when you're relying on that, right? And just in the interest of kind of transparency and perhaps for debugging. And so one thing that we did was also kind of propose a very simple model for named entity recognition, which explicitly sort of separates the context and the local word input, and then kind of puts them together at one point in the model using a gating mechanism. And what this allows you to do is try to tease out the contribution of the local word input versus the contextual input. So you can kind of see when I make correct predictions for entities on sort of average over the span corresponding to that entity, what you observe, or what one observes, is that it tends to rely quite a bit on that span, and when it makes incorrect predictions, it relies kind of less on the local inputs. And so again, I think maybe thinking about sort of how we can design architectures that explicitly allow you to know on what systems are making predictions on the basis of is sort of a promising direction. Okay, so I'm excited to move on to questions. So I think I'll stop here, and thanks for your attention, and again, thanks for the invite. And yeah, happy to chat more.
Okay, thank you so much, Byron, for this great talk. I see one question in the Q&A section so far. I can invite more people to ask theirs. In the meantime, I can read out this one. It's from Sarah. Thanks for the great talk, Byron. I'm curious of your thoughts on using or borrowing interpretability methods from fields without discrete inputs, such as computer vision. Namely, gradient-based or perturbation methods create small changes to the input. In NLP, these no longer represent real or observable data.
Yeah. So I think the question is about sort of the interpretation of discrete sort of, I guess, rationales in general when you have. So are you saying in images? So basically applying something like discrete rationalization to images? Is that the idea?
So fields without discrete inputs, such as CV. So
I see. Yeah.
There is no the inputs are continuous, and in NLP they are discrete. So
yeah, it's good. I really don't. So I'm not super up to date on what folks are doing now. So in this, I mean, my sense is that in some sense, maybe tracing back, like the activations on your convolutional neural networks or whatever, assuming that's what folks are still using in vision, is actually like a little bit more reasonable in the sense that these are just like feed-forward networks, and so you sidestep a lot of the complications. But I haven't really thought much about it, to be honest. So I don't know. Maybe something like doing discrete selection would be really interesting for some cases in vision, but I don't have a good I don't have a good intuition, but I'd be happy to brainstorm about that if somebody's working in vision and interested.
Okay, thanks. Okay, there's a new question on the board. Thanks from Anonymous. I guess they can say their name if they want in the response. Thanks for the talk, Byron. What are some practical applications of interpretability in understanding human languages? Can it be used in generating that language understood by all? Not so clear on what.
Yeah, well, that's a broad question. I think I don't know. So I guess in terms of applications, I could start there. I mean, I think there's lots of I think increasingly we're going to need to think about human elements. I mean, we should already be doing this, and many people already are. But I guess interpretability to me kind of goes hand in hand with how systems interact with humans, and I usually have in mind kind of domain experts. And thinking about the kinds of varieties of interpretability that they want, I think will become kind of increasingly important in this subspace, and maybe refining our definitions so that they align with typical kind of desires of end users, if that makes sense. I can't speak. So in terms of the language component of that question, I think maybe what the questioner is getting at is there is like a body of work that's really interesting, not what I'm really working on, but that looks at using, I guess, interpretability methods broadly construed to maybe use machine learning as a mechanism to actually understand what's going on in language use. And I can't directly speak to that other than to say that I know that there's a lot of super interesting stuff going on in that space, but I don't know if I've answered the question at all.
Still very interesting. I think I'll piggyback off something that I kind of read between the lines there. So everything you presented was in English or about English?
Yes.
Is there any cross-linguistic directions that you can think of that would make it? So for example, English has a very preset word order, right? It's very rigid in its word order. And when you use attention modules on these RNNs or these the LSTM sequence taggers, then we're very much married to the word order part of the system. And in other languages, this might be much more free, right? Or
yeah.
You think about other ways in which this would be different across languages.
Yeah, that is a really good question, and you're right. Yeah, I'm sort of guilty of privileging English here, So I can't say I will further sort of make myself guilty. So I can't say that I've actually thought too much about it in terms of, but I should. And I think it's interesting to think about the degree to which these sorts of interpretability methods are tied to specific languages. Your point about the sequential structure is a good example of that. But in all honesty, I haven't thought much about it, but I completely agree that it's an overlooked and very interesting direction. And I don't know that I have anything off the top of my head smarter to say than that.
Okay. I think we have 5 minutes left. There's one more question. I see that there's yet another new one, so I have to quickly decide which one I'm asking.
No.
Yeah, let's try this one from David Kartzner. I hope I'm saying that right. Right now, many systems try to generate explanations for network predictions. How could models be trained to go to the other direction, i.e. from explanations or salient scores to labeling rules for unlabeled portions of the data set? I like this one.
I think that's cool. I think that's a really good idea. So I don't know of a lot of work that's trying to do that, but I think this notion of maybe what you could do is derive these sort of explanations or whatever rationales, what have you, and then kind of compress those in some meaningful way by inducing rule-based methods, which I think is what they have in mind. I think that would be cool because you would have kind of you sort of go back to these almost rule-based systems that are somehow derived from these really complicated neural networks. And I don't know, I'd have to think about it more, but it seems like there might be something interesting there. But I haven't seen it. So I think this would be a line worth pursuing.
Yeah. And I think this last question actually has to do with my follow-up from before. Would saliency maps, from Amanda De Souza. So would saliency maps and rationales work in the same way at subword levels as they would or do for tokens?
Yeah, that's a good question. So I think in our work I think this is often glossed over in English anyway, right? Where you kind of do some sort of a pooling over the subword tokenizations, because of course we don't think in terms of subwords typically. But sorry, was there another part to that?
That was it.
Okay, I thought you were starting. Yeah, so I think we sort of gloss over this a lot. It might be interesting to kind of do something more explicit with the subwords, but it's not immediately clear to me what you would do, right? Because I think, at least in English, we think in terms of word units, and so doing anything other than providing highlights. Well, I mean, it might expose like artifacts, right? Like you could imagine that. You could imagine cases where, there are certain roots or something like that are, or even, I don't know, like maybe the system is picking up on pluralization or something like this, or past or tense, for example. And it's possible that like sort of thinking about subword level explanations would be illustrative there. But I haven't thought much about it, but it's typically we could sort of gloss over this. So there may be something there.
I can add that at least for some tasks, this work is being done. So there is there is a line of work about at least character level things within sequence taggers, for example. So part of speech tagging does indeed attend to different subword levels.
And that actually gets like you were saying, get back to the earlier question about like that might actually tell you something. I'm just speculating here, but that might actually tell you something about like sort of language and how and provide insights in that way, which might be interesting.
Yeah. If we have like a minute or two more, I was interested in knowing more about how these things, mostly the influence functions work. So if that has effects on exploring model bias or data bias, is there applications in that? Because you mentioned bias in the intro to your talk, and I was wondering how that actually.
Yeah. I mean, I didn't really follow through with that, I suppose, but like, I guess what you could hope is that, I can imagine a couple of ways of doing that. So, I mean, the most obvious way would be, if you surfaced, the most influential examples and they, sort of all prominently featured, let's say, features that were sensitive in some ways, right? And that were, I guess, indicative of like a protected category or something like that, then you might be able to spot that in a way that wasn't really possible before. The problem with, I guess, this perspective is, and maybe with influence functions, it's not really a problem, but just one of the things that makes it difficult is a lot of this depends on having the human in the loop, right? And I think that's also its strength. But basically, you're relying on human intelligence to look at the training examples that were influential and kind of perform some sort of a synopsis, right? And I think it would be nice if we had kind of methods for doing that. But yeah, so I think aside from that, maybe what you could do is try to drill down on the influence to see like what actually was sort of salient within that feature, right? Or within that input, and maybe that would help expose if it's relying on sensitive features as well. So I think there is opportunity because, if it's the case that the influential examples correlate with the protected attribute that you care about with respect to fairness, which you could analyze quantitatively, then you might have a problem, and that would give you kind of pause. And so I think in that sense you could use something like similar to the approach we did with just the token with the sort of saliency versus influence functions, and instead of looking at sort of how the influence breaks down with respect to sort of the most salient tokens, you could look at it how the influence breaks down with respect to the classes of interest that you might be concerned about.
Okay, yeah, that makes a lot of sense. So we're just closing in at 1 hour. So let's all thank Byron again. This was fascinating talk. Thank you so much.
Thanks for having me.
And yeah, and
if anyone wants to follow up by email or anything like that, yeah, easy to find. So please do.
Okay, and we'll see everybody in the next seminar.
Thanks all.